Okay, so we're going to have a review, and for those of you who weren't here the past 2 days, this will be maybe new for the review. I hope you're going to watch and say, yes, yes, I get it, I get it. Nico's going to go through this. Come on up, Nico, a little bit faster. We should have a quiz at the end as opposed to having Nico do this, but this is for those of you who weren't here the last couple of days. Our fundamental issue is how do we sample the space of ground motion models, thinking of it as just discretizing a continuous distribution. And it's a higher order thing, so it's been more difficult. So what Nico is going to talk about is the way to try to do that we think it gives us a framework to evaluate this problem, right? How we can lay things out in a common approach. So again, I'm hoping for the rest of you, this is going to just say, yeah, easy, right? Like you're taking class the second time, it's always easier the second time through. Go ahead. No.
All right, so
we can get questions from the yeah, questions are okay. I want to make sure if you're saying, wait a minute, that's not how I understood it, interrupt us, okay? So questions are all right. If we go a little long, this is fine because we actually have, we've got room today to spend some more time on this if we need to. For those of you who weren't here, Jack and we lost Ed. We've got to get him back before we run through all this. Interrupt, okay? I don't want you to say, I have no idea what they're doing. We want to get this so you understand the concepts, okay?
all right, so this will be the same talk I gave on Monday because I was asked like this morning to give it again. I go through it very quickly, so we're not going to spend a lot of time of the details, just about the general approach, I think. And so the motivation for the approach is this. Think of this square as the model space of GMPEs. So this is just some abstract representation of the model space, and each of these red points there is an actual GMPE. And now what you see is these are just points in the model space, but the model space in general is just much bigger. And the question is, why haven't we points where we don't have points? So basically what we think is something like this. There are a lot of different possible GMPs, they just haven't observed yet. And the reason is that NGA employed 5 developers and not 10. There's a limited amount of data. In the future, you might have not very different data, but just different data, which might give rise to a different GMPE. So the question is, to really appreciate the center, body, and range, we somehow need to get these gray points to the unpublished models when we only have the red points. All right. So the assumption that we're making is that each GMPE is actually a sample from a distribution of GMPEs. So the observed GMPEs are a sample of some distribution of GMPEs, and we somehow have to get to this distribution. So how we're going to do that is we're going to take the selected GMPEs, fit them to a common functional form. Then from the common functional form, we have a set of coefficients for each GMPE. From this set of coefficients, so imagine we have 7 GMPs, and we have 7 sets of coefficients, and then we can estimate the joint coefficient distribution. And from this joint distribution, we can sample new sets of coefficients, and this means we can generate new GMPEs. And then in the end, we have maybe sampled this whole space of gray models, and then we need to think about how to reduce that. Which of them are physical, which are credible, which are not. That's the job of the TI team then. All right. So this is just the same thing. We should think that each GMP is a sample from a distribution, which will in general be very complicated because the GMPEs are just very complicated. But if we simplify every GMPE to a common functional form, each of which has the same coefficients, then this GMPE distribution reduces to a distribution over the set of coefficients theta. And then A further assumption is that this distribution over the set of coefficients is multivariate normal. And then we just need to estimate the mean of the coefficients and the covariance of these coefficients, and then we can sample from that. So this is actually the whole approach. And I'm finished.
We're done. So, sounds very abstract, but Nico is creating more models based on trying to see what the range of the current models are, but you're also going to go outside that range because he's going to create this thing on the bottom. That's really the whole thing. His coefficients. So now we all have the same coefficients. C0, C1, C2 all mean the same thing for each of the models. And he can say what is the average of the coefficients. That's the mu sub theta. Okay, so that's kind of, if I took them all and said, I'm going to average all your C1s, I'm going to average all your C2s. Well, that's really not what we do, but then he's going to work on how those change, the covariance, which is the trade-off. If on one model I push C2 up, well, C3 adjusts coming down, right? So he's going to have that trade-off in there through the covariance matrix. Okay, and so now sampling that, his big assumption is these are normally distributed, right? So we'll start, Jack, I want to make sure, and Ed, that that's making sense to you what you're talking about here.
So, quick question, when you fit the new model with this common functional form, you have to pick the set of predictor variable conditions under which to do that fitting.
Yes.
And presumably if it was all moderate magnitudes, moderate distances,
Yes.
everything would fit, very
So this will
consistently.
be.
How do you pick the range of conditions for which to do the calibration?
So this will be done based on the sources that are relevant.
From the deaggregation tells us where to focus it. So we can live with misfits in areas
Right.
that aren't as important. Okay. Adrian? Ken?
Why couldn't you, to address the issue of correlation between reverse and strike slip, why couldn't you fit a style of faulting factor that has a common functional form for all models and find the correlation of those parameters as
Well,
well?
the style of faulting factor for reverse faulting means is not just a factor. It's not just scaling up and down because it's the hanging wall term.
So Adrian,
Yes.
for Arizona, we'll probably do exactly that for the host zone.
Is the check eventually made with the data?
Yes.
Okay, just to be sure.
So
Can you repeat the
if
question,
you're,
please?
if you're, for those of you who just got here, the microphone has to be like you're a rock star, right? So right in front of your mouth.
Like you're,
You just have to put it closer than you think
Yes.
you really should. It's Ken.
So just to be clear, I mean, I understand this from seeing it several times, but you're just, the distribution of the coefficients includes only the distribution of the, taking into account the median estimates from the 7 models that you
Yes.
fitted.
Yes,
So it's
right.
does not have within model epistemic uncertainty also included.
No.
Yeah.
At the moment,
Will
Yes.
it?
Within model epistemic uncertainty. So is this,
that would be Bob's and Linda's model.
yeah, that you could add in and then create.
Well, you say you could. Will you? Or have you-
Ideally, to do that, you would have the
Can you jump to your distribution
Yes.
plot?
Okay.
He's addressed.
Anyway,
No, I mean, ideally, to include the epistemic uncertainty of the models, you need the covariance of all the parameters of the models. Because the epistemic uncertainty is not just shifting it up and down. This is probably the most important part, but it's the uncertainty in all of the coefficients. And if you're just shifting up and down, it's just the uncertainty in the
so that doesn't
bias,
easily
right?
fit into your
Right.
framework here? Is that the issue? It may have to be treated after the fact or something like that?
I mean, you could include Bob's and Linda's model for the NGA models and just shifting them each curve up and down and then fitting it. But that will only affect one parameter. Well, two fully large
yeah.
distances. But
Well, the epistemic model is relatively simple, but
Yeah,
still.
and we do
Right.
need,
I understand it adds
But
another complication, but it seems like it's,
it's straightforward to create, to use that epistemic uncertainty to create from, instead of 7 models, whatever, we would create 30, and then you
Right.
now
Yes.
do the same covariance, and that problem, we
Oh,
would broaden
okay.
it out. But if you remember on Monday, Nico showed the range that we got from Bob and Linda's model compared to the range that he's already creating, and it is much larger. But your point being that smaller range applies to each individual model currently, right? I think the plan is we need to make sure it's captured.
I mean,
But
we can add it. We'll just broaden the distribution a little bit. In the end, it gets reduced anyway. Well,
so we think the distribution is pushed out, and we're already going to be chopping from the edges, is what Nico
Yes.
is getting at. So we could push it out further, but he could also run 1,000 or 10,000 models and push
yeah,
it
I
out
could
further.
if I sampled the tails of this distribution, then I would.
But
get
I
at
think
the
we
same
need to
base.
we need to demonstrate that we are bigger than that range, right? Because that's a minimum range from what the models themselves have.
All right, Tom has.
No, this is
then-
Linda.
And then when you,
Hold on, Linda. Go ahead, Tom.
Yes.
when you get all these models, do you test them against the data again?
That's where we were. I think the answer is yes,
Well-
and you'll see that. So hang on.
And so my next question is, if you test them against the data, how do you sample the data? Because there's many more data for smaller earthquakes than there are for larger earthquakes. So if you just sort of took that to the nth degree, you'd be fitting all the smaller earthquakes, and you wouldn't fit the big earthquakes at all. Who would care? Because there's so many more data points at the small ones. How do you handle that issue?
So the way we're doing it right now is because we're fitting the functional forms only for magnitudes 5 to 8, or 5 to 7 in the normal case, because that's the important range for hazard. We select only the data in that range.
So do you try to re-normalize the number of data for 5s versus 8s, or do you just take all available for 5s? Or
Right now we're taking all data because there's not that much data. Well, especially, it's not so much the magnitude range as the distance and VS30 range that reduces the data. So right
basically, you're putting Gutenberg Richter in twice when you do that, right? So because there's the actual data's already got Gutenberg Richter in it. I mean,
It actually really doesn't. So our ground motion data, surprisingly, is not scaling exponentially with magnitude like a Gutenberg-Richter relation would do. And the way we're handling this, Tom, is looking at different subsets of the data. 5s and larger, 6s and larger, and so forth. We haven't gone to, say, 5 to 5.5 or so forth, because we run out. There's just simply not enough. So we will use at least 2 ranges, bigger than 5 and probably bigger than 6.3, so that we still have something to work with. But we really don't have 10 times the data at the smaller, every magnitude in strong motion data sets. That's not how it's worked, because our focus has been on the big ones, and we've kind of ignored a lot of the small ones.
I see. So it's kind of an ad hoc resampling of the number of data points fit as a function of magnitude.
Yeah, and it's really from the data that we're reusing the data that were used to derive the models. So it's almost those same things. Part of this was, Ed had said, where's the sanity check? Does this fit the data again? So we want to be sure we've created these new models, and they are, in general, consistent with what the data are, so that if you had derived those models, this is from the data, that's what may have come out.
Okay, thanks.
Okay. Linda?
Yes. Can you hear me?
Yes.
Hello? Yeah, I just wanted to say that what you described in taking one model and creating 3 out of it before you start might be a good idea. The other thing is you're starting with the 5 NGA models plus 1.
Linda, hold on.
Extra.
Wait.
Yeah.
You need to slow down. And you just said something was a good idea, and we're not sure what was said was a good idea.
I mean, you said the way to incorporate the epistemic uncertainty might be by taking each model and making it 3 before you start your fitting.
Yes, and that's you're saying that would be a good idea.
Yes.
Okay.
The other thing I'm saying is now you are working with the 5 NGA West 2 models plus 1 or plus 2 additional ones. I can't remember.
Plus 2. No, plus.
Okay.
Yeah.
So your uncertainty just by having these additional ones might be already bigger than the additional epistemic uncertainty, because when Bob and I did it, we compared the uncertainty within each model to the uncertainty, to the model-to-model uncertainty of taking the 5 NGA West 2 models. So now your model-to-model uncertainty will be even bigger than that.
Yeah,
This is the fast version of all this.
this one.
Right there.
This one.
Yeah, so I'm just
So
saying
it's
that
okay.
even from the beginning, you might be having even more epistemic uncertainty.
Right.
You might need to check, but.
So
yeah,
this
that's it.
was jumping to the end to say these green and red curves are Bob and Linda's estimate of the epistemic uncertainty in the individual model. The gray one is what?
So basically, this is just shows the end. So this is a plot of the original GMPEs in red, the fitted GMPEs in blue, the Greiser and Calcam, which was not used to fit, in green, and 1,000 sampled models. And then the next plot, this one would be just a slice through that distribution. So the histogram are the 1,000 newly sampled models. That would be the epistemic uncertainty of all these new models.
Right.
And then we have the red and the green line are the epistemic uncertainty of Bob's and Linda's model centered on the highest and lowest GMPE prediction.
Can we go back to the previous slide that showed the functional for
This one or
way,
that one?
way back where you were
Yes,
before?
you're right.
Before you
So-
jumped all these.
Right, so we're just coming back.
Now,
Uh,
no,
this
the one they had back before
back.
that. Back. There you go.
So we were.
You have this equation here, which is the one you're going to fit. And
Yes.
you're using various parameters, various variables to fit to. When you look at the GMPEs that are currently available, each one has done something different from the other.
Yes, so
So what is the basis for your selection here? Are you going to take the one that has the largest and use that, or the one that has the smallest? Because that could make a heck of a difference. And he uses something related to VS in a different way from the way he does, and so on and so forth. And some use the top of rupture, et cetera, et cetera, et cetera.
That's true. So
How is that being selected? I know how it would be handled once you select it, but what is the basis for your selection, really, is my question. Where is the judgment coming in?
that's where the judgment is coming in. And so how it is selected is it's a bit also on convenience, because they're actually, I mean, even though, so this is for the strike slip case, even though the models treat many things differently, this will only be evaluated for one VS30 case, for example. So we don't care about the VS30 scale, different VS30 scaling of the different models. We definitely lose something, but as we've seen in Nick's presentation, that doesn't really matter in hazard space. And the only thing that really matters in terms of fit is the different distance metric. So basically, joiner-Boer distance versus rupture distance. That actually matters.
And the depth matters as
and
well.
the depth matters.
So-
Well, yes.
We discussed it a couple of days ago. If there is no, I know. So if there is a specific, important, unique feature of one of the GMPEs that it's not there, they are going to rerun the thing with that specific feature. The example is RGB versus RRAW. You cannot do it both in one.
And it's surprising, I mean, I shouldn't say surprising, a simple form, you could adopt any one of our models and it would work pretty well for the others. Things aren't fundamentally that different.
It's not really how you handled each variable. It's what independent variables entered in here.
So go to your
Yes.
equation and you will see.
That's the.
So
Because
he-
then once
so-
you've decided on which variables to include as an independent variable, then the data will help you fit the coefficient, I assume.
We're not fitting data.
You just,
We're
You
using
fit-
the
you fit-
models
you
to
fit- you
generate
fit-
their medians, and we're
to
fitting
fit,
the
to fit
median.
the median of the relationship.
Yeah, it's
Then
much
we have
simpler.
a lot of degrees of freedom then.
We can generate a whole lot of points,
Much more
right?
degrees of freedom.
We can generate as many as you want, and they're smooth already. It's a much easier process.
Why didn't I do that?
Okay, so this is just a question? No, this is just the example for the strike slip case where there are 7 GMPEs, 5 NGA models, the Zhao et al. 2006, and the adjusted Zhao and Lu model. And so what I did is I evaluated each GMPE for magnitudes 5 to 8, for Joyner-Boer distances from 1 to 70 kilometers. I had for each magnitude 3 values of depth to the top of the ruptures. From that one I can calculate hypocentral depth. VS30 is 760 meter per second, and it's a vertically dipping strike slip fault, which makes it easy to calculate Joyner-Boer distance and rupture distance, and for 5 periods. So each of the 7 models gets evaluated at these magnitude and distance values. Then I have a large data set for each magnitude and distance, for each GMPE, and then that data, well, that synthetic data gets fitted to a common functional form. Is that?
Yes, so I get that. I mean, just stepping back and thinking, we had ways of representing epistemic uncertainty in GMPEs before this. Now we're changing to this new model, this new way of doing it. And sort of reflecting on what you've said and thinking about the overall picture, it seems to me that there's 3 hurdles to get over for people to understand what you're doing and for the whole process to be sort of accepted. And some of these we've talked about, and maybe some of them we haven't. Seems to me number 1 is how well does your model, your functional form that you're using, capture the original models? And we've talked about that. We've seen it in the hazard space, but what we haven't seen the last 2 days. Maybe on the first day you showed it because I wasn't here, but individual, like here's a magnitude 7 strike slip fault, and here's what it looks like, and seeing it at that level we haven't quite seen yet. But I think that's pretty important. How well does it capture that? The second issue is when you do this sampling of the covariance matrix and produce 1,000 models, it seems to me that there's a pretty high probability that some of those models are just non-physical. Now maybe we have to accept that. Maybe that's the whole point, is to get things that are all over
Talked
the place.
about that a lot on the first day, yes.
Okay.
And how we might get around that.
Okay. Yeah. So
That's
key,
an issue. That's an
step.
issue, yeah.
And inevitably, that seems to me to be a really tricky one, because how do you decide what is non-physical? Different people would draw that line in a different place, I'm sure. So expert opinion would come in there.
It's more than non-physical. It's also such a low likelihood. We get to the point that it violates our observations.
Right.
We have some things where we can say, look, you can't be here, and you can't be there, and that's so the range is pretty broad.
Right.
But we are creating models that probably violate that. And we're doing that by the check again against the data. If the mean bias is so large from the data, or when we do the likelihood, we can see it's falling off the cliff of the likelihood function, we would exclude those models. We have to do that part.
Right. So there's some way of making that judgment with the likelihood function or whatever.
Well, and the mean residuals, and we do it for alternative subsets, so it's not determined by just one set.
Right. And then I think the third issue, which I think a lot of people are struggling with, is even if we accept the first two, you're fitting the models adequately, and whatever range you pick is fine. When you condense down this, who knows how many orders space into a plane, and the values of the axes on that plane don't have any physical meaning, and we're trying to figure out what it means to have a GMPE in various places and the gray dots in many other places. Just how to interpret that is tricky. And I know that there's signposts and magnitude scaling maybe goes this way and distance goes that way. But could it be that the magnitude scaling and the depth scaling are actually going in the same direction or so close that you can't tell? So
Yes.
those are just examples of the broader question of how do we interpret that with respect to all those controlling variables that we know to be important. And that's a non-trivial step. We've kind of seen anecdotally here and there, it looks this way or that way, but it seems to be very anecdotal, not systematic, at least for this observer, to know how to interpret that. So as I look at this sort of new way of visualizing epistemic uncertainty, I think those are the three key hurdles to get over.
Tom? So while we're getting it, what you're talking about is what we spent the last 3 years trying to get to. Okay, so and I think we are dealing with all three of those issues. The last one we'll bring up again today and spend a little more time looking at some of these when we put the candidate, how do we grab 9 of the models or 10 or whatever it's going to be? What do they look like? So we'll show you a few plots of what those are. And then the exclusion comes back to, again, getting so far out that we violated the data. And interpreting those maps, it's just, it's similarity of a distribution. If I gave you a normal distribution, I say now please discretize that to 6 points, there's different ways you could do it, right? You try to make them 6 equally weighted, or you could try to get to the extremes and say I'm going to have low weights on the ends, but I want to sample the whole thing. That's all we're doing. We're just trying to take the GMPE that you could create and turn them into a space that we can chop up. And instead of one-dimensional like you have in a Gaussian, it's two-dimensional. We've had to, you have to lose something going from higher orders down to 2D, but in 2D now we can carve that up and say, yes, here I am now discretizing the range of possible models and assigning weights to them. That's really what you should be looking at those maps as doing. And their location on there, they're closer together, means that they're in their ground motion predictions, they are similar, right? If you want to think of it as we call it the distance between it, but it's like the variance between the models, right? If I took their differences at each one of those points and just said, show me the standard deviation of model A versus model B, the smaller that is, the closer they are on these plots. The further away they are, the difference they are. So I think there's something there. You just don't want to say, oh, it's 2, okay, or it's a 1 on that x-axis, and maybe we shouldn't even show the axes, but I think it's still helpful to see that it's either square or do we have the same directions in the x and the y, but how do we get out there and how do we then define this region that we want to now discretize into a manageable number to use? Is that making sense, John? Well, go ahead, Tom.
So Could you go to the slide with the actual common functional form? So in that, it's broken into different magnitude bins, and could you go through how how that works? You've got a A0 and
So we
an
have
A8 term and a A9 distance, depth. So these are all power laws, and then you've got all these other terms in there. Some of them depend on magnitude. One of the critical issues is the cross terms that are terms that depend on both magnitude and distance.
That's actually not something I'm worried about because that is common to all GMPs. So the cross term between magnitudes and distance, which is this, where is it? Oops, sorry.
Well, can we look
There's
at where
one,
that term is?
That part. So this, that's the A5 plus A6 magnitude times log of the distance.
It doesn't look like it's there for magnitude less than 5.5, or I can't tell. What do those magnitudes less than 5.5 mean? Is that?
So the reason why this is just to ensure continuity, so that it's so this magnitude dependent distance scaling will not really show up that much for the small magnitudes below 5.5.
But that's not true. I mean, it does show up. It clearly does show up. We see.
But Tom, this is you're over complicating it here. This form looks the way it is. It's a piecewise linear form with a quadratic added. But think of a piecewise linear, and we need to make the pieces continuous.
Okay,
and it breaks at 5.5 and 6.5.
But below 5.5, there's no cross term. Is that right?
No, there is.
No, but the cross term in that case is constant.
Yeah, but it's a constant, so it isn't a cross term.
Right.
There is no cross term.
But we only need it for magnitudes 5 to 5.5. There is no. It's a small enough range that a constant is fine.
All right.
This won't work for a magnitude 3.
Right.
And maybe we should have written M5 to 5.5 or something like that, so that it's clear.
And then for the 5.5 to 6.5, the cross term is this A6 NW times the log of the distance.
Right.
Yes.
So.
If you actually look at all the 5 NGA models, they all have this exact term in there. So, and this is one of the reasons why it's chosen, because it will fit the NGA models.
Yeah.
Right. Okay.
And this is what we're doing. We're not fitting data, we're fitting models. And we need to capture the models as good as we can. And if we assume that the models fitted the data, then we're still losing something because we're slightly different, but, right.
So,
Yes.
Nico, I
Yes.
think one comment and one question. The comment, correct me if I'm wrong, this is for specific sites. You're not generating from magnitude 3 to magnitude 9 and so on.
5 to 8.
Exactly. For that specific site, that's really the interest.
Yes.
Then my question is that how many minimum seed GMPs you need? You started with 7. How many minimum?
Well, 7 is actually, it's already a low number.
Okay. No, in
Right,
fact,
no.
that is good.
Yeah.
So I want to, that is, I want to make sure that it's not 1, really, because that
Well, with
creates
1, I
19th
can
century.
generate, I can fit that, but I
Distribution
cannot
with
sample
1.
from that.
Should also point out that there are a couple typos in this equation. A4 should be multiplying the term as 8.5 minus m, not 8.5 minus 5.5. And
So that's only for the above 5.5. That's the case.
right, but
Yes.
This is Robin. Can I ask a question?
Sure, go ahead.
Maybe go back to the slide with the original GMPs on it, maybe the previous slide, just listed.
Can you go back one, Nico? There.
Yeah, that one. I think one limitation that I see here, and tell me if I'm wrong, is that you cannot put weights on these original GMPEs. So they're equally weighted. And for instance, if you had a published ground motion equation that you said, well, that's pretty crazy, but we should give it some small weight just to make sure it's in the model and see what effect it has and say that we represented it, you can't do that. Is that correct?
That's correct, but we're going through new models. We're just using that to generate the model space, and in the end, the weights will go on the model space. And if it's really crazy, it will show up in the tails of the distribution, of the coefficient distribution, and it will get afterwards, after we've gone through the whole analysis, it will get a lower weight.
Nico, I disagree. I think what keeps you from assigning weights and then compute the mean and the weighted mean and covariance matrix? I think there's nothing.
We could do it. He
You could do
hasn't
it.
done it.
He has not done it, but in principle, I think there's no obstacle.
Right. But the other side is we have selected these already as models that are
Exactly.
acceptable.
I agree. And
so
they all went through the same process. They had more or less the same pedigree. So there are good reasons to make it constant.
Right.
But I think methodologically, there's no reason to make that weight constant.
No, that's true, but then you have to go through this whole thing again. How do you assign weights to the GMPEs? And how do you say this one is more credible than the other one?
So you're weighting it twice.
Yeah.
And this is a complicated issue.
No, I agree.
Weighting the
But
GMPEs.
methodologically, I think it's okay. I
You
want
should
to
talk to Brian about that.
Okay. Now that that I have.
Let me finish, please. Gabe? Let me
Go ahead,
just
Roy.
comment on Nico's response. And let me comment on Nico's response. I think you said that crazy attenuation equation or ground motion equation would be recognized. I don't know how you would recognize it because you are fitting to the estimates from 7 equations. So you would give that 7th equation as much weight as you give number 1 and number 2 and number 3. So, you must give it 1/7 the weight and respect it as a credible model, but in the back of your mind, it may have very little weight.
But Robin, we set the weights of our sampling of this space that's generated later on, and we compare to the what we showed on Monday, the means and or yesterday, the mean bias from our various subsets of data to these models and the likelihoods. So when they're far off, even though they were created by this process, they are excluded. This is really a way to make a bigger space that is sort of continuous of models.
But the likelihood is based on the estimates. It's not based on data. This has no relevance to data.
That's not correct. The likelihood calculations that Nico shows are the likelihood of this particular model, each one of the 1,000 done separately, of having produced our selected subset of data. That's where the questions came up. Where do we check with data? That's where it happens. Those contour plots on the back are data. We haven't got to those yet, Ed. But those
are not ground motion data, as I understand it.
They are ground motion data.
No, those are not ground motion data. Say that again, please.
No, we're actually, in the end, we're comparing it to a subset of the NGA data set, to a subset of maybe the European data set, and any other subsets that might be selected.
Yeah, but you haven't gotten to that in this presentation.
Yeah. But let's make it clear to everyone, the contour plots in the background of the Salmon's maps are data. Different kinds of models. We have median bias and we have likelihood. And then we could do that for a different subset and see repeatedly this model to any subset is way off the edge. We don't use it.
I wanted to make one comment related to that. I think you probably do get crazy models or non-physical models in the 1,000 point sampling, but I think if you do any sampling that is more systematic, you are less likely to get those strange points.
Yes, we talked about that.
Yes.
We're going to adjust how we sample and how we fit. So this will not be the
So that- yeah.
final functional form.
Exactly, that may
But,
be less of a problem
right.
later. The other comment I wanted to make as a suggestion, I think you can do it. In the Salmons map, my understanding is that these maps are rotationally invariant, right? You can rotate
Yes.
it. So it may make sense to arbitrarily decide we're going to make the up-down decision the scaling dimension, and always rotate them that way. So people start getting used to what it means to move in one direction, up, down versus sideways and so on. It's arbitrary, but at least it helps our intuition.
I can probably do that. I need to.
I
think.
think
yes,
that's a
yeah.
really good idea. So we could set it so, you know, horizontally is always in the median change direction. Okay, that would and that would always come up. That would be something for everyone to hold on to, right? I know going left to right is changes in the constant factor, right, between them as a way. The other directions will be magnitude or distance dependent, will not be common. We can only do that rotation, and we can do it one time.
But at least you can flip it. You at least flip the other one, right? You can rotate one way and then define positive and negative in the other direction in a convenient, intuitive way, I think.
So we could try to make
Yes.
the going up,
Exactly,
it would have to be
meaning that
one
up
direction
means the
in
same
the
thing. Yeah,
magnitude
that
or
up means the
distance.
same, or either the same thing or more or less the same thing.
Can I ask a question? You're doing this by using this value for these 7 relationships. And you're fixing 3 of these to wherever they apply.
Yes.
So then when you make the comparison to the data from this realization, how do you select the data that correspond to this, since there aren't that many? I'm not sure there's any at 760.
So the way
But
that we-
regardless, are you selecting a range? Is that how you're
well,
doing?
at first we were selecting a range, but then we were correcting the data to 760 meters per second.
By whose relationship? All 7,
I have to,
averaging out? What's going on
norm.
here?
We set a subset of the data used by the different relations. So we'll do this, say,
No, it's
for
about
NJ
the correction of the BS30.
Oh, the correction
that
of
I got from-
BS30, yeah. In this case, we used the correction that I had. We can do it several times, but that's not the big issue here.
Okay.
If I did it using any of the correction methods, we will get about the same result.
I think-
Because remember, we're not fitting the fundamental data at the
No,
end.
I understand that, but you have to have a check to make
Correct.
sure that whatever realization you got makes sense.
Right, right.
And
So, and I think the way that we will do that is with each of the GMPEs, we will use their subset of the data and their correction method,
okay, gotcha.
right? And then we can do that and have it all consistent that way. Because I don't want to do everyone's correction method with everyone else's case, or I'm going to have
Sure.
too many to work with.
Okay.
So back to Robin's comment on weighting those 7, I think one possibly good example is yaw. Again, since the large magnitude is of interest and we know that the behavior of that model at large magnitude saturation is a little bit, how do I say it, strange. So by including that without any weight, so it may distort the whole distribution. I don't know. If you reduce it by some weight.
But let's say we change the weight. Let me try, Nico,
Yes.
and then you can correct me, because we would change the weight. It's still in there. That's just going to change how many models go in a certain direction. I don't care, because I'm just dividing up the space, and I'm now going to re-weight in that space based on what is going to be fundamentally subjective evaluation of how those models are consistent with the various subsets of the data and
So-
as they move. So
I
it
mean,
doesn't
you said-
matter.
Think about it this way. It might, so you will include it, but then in the end, because it's fundamentally different from everything else, it will be somewhere on the edge
No,
of my
that part-
1,000 models.
that part-
And then you say, I don't care about this particular range of my model space.
No, in fact, that's the beauty of the whole
Right.
process. That part I agree. The only thing
So-
is that hypothetically, from the 7, you exclude jaw, hypothetically, you have 6 and repeat the process. I want to see the impact of that.
He's done some of that.
Oh, you did? Okay.
So I've done the same thing using only the 5 NGA models. And you'll get a very similar range of model predictions.
So that's fine.
Yeah. This initial part, giving them equal weight, is not a weighting exercise, right? And we're trying to avoid that. We don't want to set weights here and have to argue them and then do them again. Okay, Bob?
Yeah, I'm trying to understand the multi-dimension to two-dimension abstraction. I'm no good at 7 dimensions or however many, 99 there are, but I'm real good at 2 dimensions and 3 dimensions. I suppose everybody in the room is. So you had a 2-dimensional plot. I understand that. It's an X and a Y without arguing what those things mean. But let's visualize instead that instead of 99 or however many dimensions were, that the real problem was only in 3. And what 3 is a cube, and I'm good at visualizing that, and I suppose you are too. So we have these models, and they have a distance in this 3-dimensional space. And that distance, we know how to calculate that analytically, and that distance then becomes how close they are in 2-dimensional space. But let's imagine that although those dimensions are different issues or parameters with the physics of the problem, that one of the dimensions is less important than the other 2. It's less important to the hazard, to the ground motion. But the distance in 3-dimensional space can't capture that because it's a distance, unless you have some way to downweight it. But let me go on. Now we have a different problem. Let's suppose we have a whole bunch of GMREs, 6 or 7, and let's suppose 2 of them are very similar in most of the, now we're imagining it's an 11 parameter space. They're really similar for 9 of them, but different for 2. Okay? Different for 2 of the 11, and we're abstracting this down to 2 dimensions.
Keep the mic close to your...
Yeah, excuse me. I have to keep the mic close. And I don't see how you can, and so you say they're similar, but they're different. I mean, if they're identical, then you don't have them anyway, unless they're just scaled by a factor of 10% or something. But they're actually different because they say something different about the physics in those 2 of those 9 dimensions or attributes or whatever the hell they are. But because of the way you've done it, you can't differentiate which of those dimensions are. Maybe they're different in an unimportant way, or maybe they're different in a really important way. And how can you tell the differences in those dimensions when you're just doing distances?
So
in
let
this
me try to
abstract
answer
space?
that for you. We do that by choosing the vector that we're going to look at to capture the part from the deaggregation of the hazard which are most important.
Okay,
already.
so that's where you, I'm not complaining, that's where you, the scientist, intervene in this process.
Yes.
It's a way of weighting or downweighting those attributes that you think are less important and giving greater to the ones that are. And you're somehow modifying that distance in this way.
And now we've used a boxcar, sort of a 0-1.
Yeah.
But you could have actually said, I want to mimic the deaggregation already and say, I'm going to have a tapering of that weighting in terms of its application to distance. So that's where it shows up.
All right, so in my 3-dimensional to 2-dimensional, I mean, that was just a simple way because I can visualize 3 dimensions. If the 3rd dimension was less important, not 0, but some less important, you would intervene to make sure that it gets that less importance reflected in how the 2-dimensional thing ends up.
Yes.
Okay, in which case, and I'm not complaining, I'm just trying to understand, in which case the central thing for outside peer reviewers to review sounds to me those interventions. That is, it's the area, it's not the only area, but it is a major area where your team's judgment needs review, and or at least understanding, because a whole lot of this other stuff may be mechanics.
Yes,
once you've picked the models, it's mechanics.
But
that's
not mechanics. Right, but there's not a whole lot of judgment on our part. I think it's the justification needs to be clear.
Okay,
but I'm going to look at deaggregations. I'm not judging the deaggregations. I've run them, so I know the hazard is controlled by 6.5s and larger. I'm not going to worry about magnitude 4s.
Yes, well, I understand that.
And so the big cutoff is easy. Now you could say, how closely do we want to mimic the deaggregation in the weighting here versus just here is the important range, 5 to 8, 0 to, for Diablo Canyon is 0 to 15. We broadened it out to about 30. Maybe that's where you could argue we've let in a little broader range than we should.
So you're answering Robin's question, and Gabe right after him, by saying that that's how you're intervening. That's a way of of weighting somehow.
No.
No? Isn't it? Yes.
You want to say that?
It sounds to me like that.
There's two places that this is happening. So I think what you're asking is how do we make the map, right? Because the distance metric on the map depends on what you've defined as the important parts.
Yes, yes.
Okay. The next part is, given where these are on the map, how do we decide which ones are credible and which ones aren't?
Okay.
That's what they were asking, and that's where you say we are comparing two data. That's what the contour plots behind it are intended to guide your interpretation. So the map is the space of values where distance is now the distance between models in a relevant range.
Is a measure of their similarity.
Correct, in the range that's important to hazard. Then we say, how do these compare to alternatives data sets? Back to Ed's earlier question, does it work? Do these still fit the data, or are they way off? Okay, and that's where we check the mean between event residual, basically the mean bias of the model, and we check the likelihood of the model to fit the observations, and we impose a constant phi and tau on there so that we're not getting a high likelihood because I blew up the standard deviation, because we know the standard deviations approximately.
All right,
so those two things now give us what we can look at to subjectively evaluate the models.
So you would agree that it's just that piece of it where peer review, not PRPP, and so on, is a place to look, because that's a place where
absolutely that's where the judgment and the evaluation and our evaluation needs to be critically reviewed in that piece of the problem. I think what Nico is saying is the way that he gets his 1,000 models is really not as sensitive to what people are concerned about. Oh, this could push it here or there. We don't need the density of points doesn't have to be at the center of where we end up putting the weights. And we'll see that on Diablo Canyon when we look at the numerical simulations. They're not going to be in the same place as the GMPEs.
No.
Do I go halfway in between where I'm going to center my model? Do I go a little towards the simulations? Do I go further towards them? That's the subjective judgment that we have to talk about. Okay? Because it's just defining what is the space.
And you're checking against two things: data, of course, and also because there's some physical, I won't call it intuition, there's some physical knowledge about the relationships between
when the models bend and go up or something like that.
You can't have bigger motion for smaller magnitudes. I mean,
correct.
Things like that.
Even we do with oversaturation, we are doing that.
I understand
that's a separate issue.
But at least you bring. Oh, thank you.
Okay, I think we need to stop. Okay, Nico.
Let me just one thing about the creation of the map that was of concern. The reasoning behind this is that you think of each model as a function, and a function is an infinitely dimensional vector. It's continuous function, so it has infinite dimensions. We're discretizing that at certain magnitude, distance, and z-tor values. And you're right, where we're discretizing matters. But we're not calculating the distance between the function at all spaces. We're calculating the distance at those magnitude distance values that are supposed to matter. And this is defined by the deaggregation.
So why don't you jump to one of your plots where you've got a contour plot behind it?
This was John's question. So this is the residuals of each model compared to the residuals of the fitted model to the actual GMP predictions. So of the new model to the real GMPE. And this shows that we're just making a mistake if we're replacing Joyner-Boer distance with Rupture distance.
Nico, I have a quick question.
Yes.
You just mentioned that it does matter.
Closer to your mouth.
You just mentioned that it does matter where you you discretize, and that you're discretizing what's important for the hazard based upon deaggregation. Does that mean that these GMPEs are only going to be good for these deaggregations, and so you can't apply them towards other plants and other?
Yes.
Yeah.
Yes.
This
So
is a site-specific model,
only applicable for strike slip in distances probably up to 30 kilometers and in magnitude range 5 to 8.
Yeah.
This is not applicable anywhere else.
Yeah, and the fixed VS30.
Right.
This is for our particular problem. If you had another site that had the same conditions, then you could use this. Right. So I think part of this, just so John would like to see curves, right? Well, that's what we'll do. Ground motion people are used to looking at residuals. Yeah, something like that.
Something like this,
Right?
in a more elaborate fashion.
Okay, so Ed's happy. Yeah, ground motion people are happy with residuals. Others like to see curves, which is fine.
Just wait, one more follow-up on that. Say you get a new seismic source model and your deaggregation changes, then these models are no longer applicable and you have to rerun the hazard with new models?
If there was a major change, yes. But that's why we have been just saying 0 or 1, 5 to 8 and 8, 0 to 30. In Diable Canyon, that's going to cover it because we really think we're good to, it's probably really 6 to 7.5, 0 to 15 kilometers, or 1 to 15 is driving it. If it became 1 to 20, it wouldn't change it. But if suddenly we had a big source out at 50 kilometers, this model would not work because we have customized it to capture the uncertainty for this application. If you wanted to make it for a broad application, you'd need to be doing this fit over a much broader range. Right? If you said, if we're doing the US for the USGS and they wanted to make hazard maps for the country, they would need to look at this in a different way, and they would have to have a 0 to 300 or 400 kilometers and all sorts of things like that. So these models and the weights that we give them would not be applicable to a national hazard map application. Is that making sense?
Yeah, but for example, maybe you discover a new fault, or there's a new fault that you have to include, like the Eastern Tennessee seismic rift fault, possibly.
Keep that really close to your mouth.
And then your hazard might change significantly based upon this new data, and so, or your deaggregation might change. So you just have to rerun the hazard, or you're gonna have to rerun the hazard with new ground motion. You're gonna have to rerun the hazard with new ground motion models. Then how do you get these new ground motion models?
If it's a real change in now, so a fault pops up that I hadn't included before. Let's say you didn't have New Madrid and then you built a New Madrid source in, you would have had to redo it because you wouldn't have been focusing on that part. So yes, but if it's if we put here, now I've got a fault at 8 kilometers away that I hadn't included, and it generates magnitude 6.2s, I say that's already in my range, I'm good.
So will the instructions here be simple enough that we can regenerate new models, or do we always have to come back to you guys to get new models?
This needs to be turned into a standard procedure that anybody can run. And before Nico goes back to Germany, he's got to get that for us.
Can't go back.
Okay, so let's talk about one of these pictures.
I think Jack has a question. Yeah? Okay.
Quick question with these projections. So when you're projecting down to 2D based on Euclidean distance, is that the same thing as principal components? Is that
something like this, but it's similar, but it's a bit more. It's based on the distance. It's not based on maximizing the variance between different.
So a quick comment is with principal components, there's kind of standard measures of how much variability you've lost in this projection, and it might be easy just to report, this 2D plane has 90% of the variance of my
But
80-dimensional.
So basically what you're doing, when you're doing PCA, you lose a lot of variance. You actually lose a lot of variance if you just go to, or you lose a lot of explanatory power if you go down to 2 dimension. So that's what it takes as input PCA, and then it moves it around so that it better captures the high dimensional distances.
But I guess my comment is
Yeah,
just
right.
that you might think about, can you report how
Something
variable
like
this
that,
plane is
yes.
relative to the high dimensional? Because
Right.
it seems like a lot of the questions are, what's missing here? And if you can say most of the variability among all these models is in this plane, that would, there's numerical ways to.
But actually, so the thing is, PCA works well if everything is linear. This is not. So basically, your high dimensional space and your lower dimensional manifold in that space is non-linear, and then PCA just doesn't work anymore. And therefore, it's difficult to do this. That's a big other issue, which is not really related here, is how do you judge a visualization? So how do you say, okay, I get this picture, does it capture what I want to capture in high dimensions? So I've taken different visualization approaches, different algorithms, and everything looks very consistent. And they're actually very different in parts. So that's a very good.
I don't know what you just said, so could you?
So I'm using, in this case, I'm using Salmon's mapping to go from high dimensions to 2 dimensions. I've also used a different visualization method, so a different method to go from high dimension to 2 dimensions. And the relative positions of the models on the map don't change.
Okay. So if you did a different approach, the ones that are
Right.
close together
The
stay
others
close
stay
together.
close together. Right.
I guess the general comment is just,
Yes,
I don't know
no,
what your metric is, but you might think about a numerical metric of what is the variability in this manifold
Yes.
versus the variability in the high dimensional space,
Yes.
in addition to the visualizations. I think there are ways that.
Do I need variability? Your
Not
question
really.
is,
I mean, we need to somehow say how well do we capture the high dimensions.
Right.
Yes.
and there could
But
be
if
some
one-
metric is what you're looking at. All right.
One other quick comment. So I understand now that you did that coefficient fitting and sampling basically to kind of sample in the neighborhood of these models, not because you think that's the kind of the final distribution you're going
Right.
to use. I got hung up on that, and I think maybe some others did, because you fit this probability distribution to parameters, and so I immediately started thinking about kind of high probability parameters versus low probability parameters. In the end, you're using that probability distribution just to interpolate, not as a probability distribution, it sounds like, and so maybe
Right.
flagging that or noting alternate ways of doing that sampling would be helpful for us understanding.
This is, in the end, the question, what do we do with the 1,000 models? And how are we go? So the basic question is, where should the ultimate distribution of should be centered, and what shape should it have? So you could say, okay, I've got a probability distribution, something continuous over my common functional form GMPEs, and you could say this is my ultimate probability distribution that I'm going to use, or you could shift it. You now have a model space to work with, and you can define a new probability distribution across this model space. And this is by comparing it to data, comparing it to simulations, and so on and so on.
Right. So an equivalent path could be to fit these coefficients to your initial models, map out some region of viable coefficients, and then do some uniform sampling across that viable region.
But
And
so
that-
the implicit assumption that goes into that is that each model is equally credible.
And that's where I think
That's
there's been a
where
lot of
we-
comments, right?
Right. But
You're-
this is if you just take this probability distribution, this coefficient distribution, if you take that as your final distribution, then you're making the implicit assumption each model has the weight that I put at first into it. So then you're going back to weighting models beforehand. And this is
We're not going to
this is a
wait.
TI team problem.
Yeah, we are not going to weight models based on their credibility. I might have several models that are equally credible, but they're similar. Okay, and I'm going to weight models to capture the space.
Yeah. Maybe my comment wasn't clear. My comment, I guess, was when you showed your initial fitting of these kind of proxy models, and you show a probability distribution on parameters, it's very hard to not interpret that as probabilities on it. And what I'm hearing now is
Right.
that you're not using them that way.
No.
But it's very
Well,
unclear
I'm
in the
not
way you
sh-
present
well,
it.
it's
So when you show
their problem.
parameters have a normal distribution with this mean and covariance matrix, put a big star and say like that's not a logic-free way.
right.
Because I think that's why I was confused for 10 minutes, and I think some others were as well.
Which
That's how you've chosen to do it, and I understand it. But
I
you might
urge you to
flag
talk
there's
to
other ways
Brian
to sample
about
it.
this.
Yes, but I think that definitely hung me up for a while, and if that's not how you're using it, you could emphasize that.
Okay.
Yes.
Can you show one where you have stuff in the background?
Yes.
Let's get to
Right, so this is then in the end how this is supposed to be used. So here, I haven't plotted the grade points yet, but this is, sorry. So this is basically a mapping of the same thing. So this whole range here is the space that's covered of 1,000 sampled models from this coefficient distribution. And then I took the subset of the ASK model of the NGA data set in the same range, 5 to 8, 1 to 70 kilometers, corrected to VS30 760.
So before you go on, this is exactly the spot where you were having trouble because we're just saying this is the viable space. Not that there's a center and that's the most likely or anything, okay? Just using to create the space. Correct.
Yes, right. And so this is a comparison of each of the 1,000 models against this subset of the NGA data set. And so the contours are mean between event residuals. So I just think I need to go back. So I took the subset for each of the 1,000 models. I calculate residuals, split the residuals into between event and within event residuals, calculate the likelihood of the data given the parameters, and then I'm just going to put that one onto this two-dimensional visualization. And this is shown what's here. So this is a plot of the mean between event residual for each of the 1,000 models. And the zero line is about here.
So this is essentially the mean bias between your real model and this subset of data that was selected.
Right. And then you could go ahead and say, okay, so this is just too high, I'm not going to capture that, or this is too low, or so this is one way to compare the 1,000 models to the data. This is within event residual, it's not really informative, and this is the likelihood.
Yeah, one comment
Okay.
I wanted to make, somewhat similar to the likelihood, but not identical. Adrian suggested that it might be useful to generate contours of the density in your multidimensional space. It is, this is based on the data,
and
that
no.
other one is
Well-
based on that model for the seas.
But that's equally weighting them, and that's the...
No, they're equally weighted in Monte Carlo. But on the other hand, once you generate them, some of them will have higher density than others. In Monte Carlo, you treat them as equally likely. But it'll give you an idea, for one thing, or before you bring in the data, how far they are, how they spread out, and how many sigmas away you have sampled, that sort of thing might be useful.
Well, I've actually done that, but this is also, it doesn't really show up very well on the map, because
Really?
what you do is you're comparing density of the coefficients, and what we're comparing here is the distances in ground motion space.
Yeah, this
And
is
that's
ground
just
motion space. Okay.
different things.
Okay.
So we're not, so this visual is not based on, so models that are close together are not based on that they are equally likely, that their coefficients are equally likely. They're close together because they give similar ground motion predictions.
Correct.
We have such a strong trade-off with our coefficients, we can get to the same point on this map in many different ways.
So you're showing us coordinate 1 and coordinate 2, and I guess I'm really stuck on, you say it doesn't matter, but I mean, why are you showing it to me then if it doesn't matter? So there must be something that describes how you mapped your space into coordinate 1. I mean, is it a linear mapping of all the A1 through A9? is what coordinate 1 is? Is it a principal?
No, so this coordinate 1 is just, it's not in any way related to the coefficients. It's related to, it's basically just related to random points on the map. So
There must be a formula somewhere that says this is coordinate 1.
Gabe, you need to use the microphone.
yes.
My suggestion is, it helped me a lot, even after listening to Nico and to Frank 100 times. Check what they say about Salmon's map in Wikipedia. Because sometimes looking at an equation really tells you a lot.
But there's not, let me try to say how I've been thinking about this, and Nico will fix it if it's not right. If I take a GMPE, Tom, just knowing that GMP doesn't tell me where it goes on this map. I can't, there's no equation that says, here's the GMPE, okay, that plots here. Then here's the next one, that plots there. This is all trying to find a representation where the distances on this map are representing the distances in the higher dimensional space.
So basically what you're doing is, the misfit function you have is the distance between points in 2 dimensions and the distance between points in high dimensions. So this is, because what you're trying to do is you're trying to mimic the distances in high dimensions with distances in 2 dimensions.
And Jack
so
was
what you're doing is, so this is your misfits. So this is your misfit function. You're trying to optimize that the distance in 2 dimensions mimics the distance in high dimensions. So this is a misfit function. And then you start with either with random initializations of points on the map, and then you're just optimizing the points on the map based on that misfit function.
Can I make a suggestion? Now that you've come up with this clever way of showing what's important in ground motion space, considering either a mean or an event term and the likelihood, maybe in the documentation in the future when you present this, just remove the coordinates completely. Just say, hey, explain the principle, the coordinates, forget about them, and then you just show this and people can only focus on the color scale. It's just a suggestion for readability and selling it. It doesn't matter?
The way I was jokingly said the first day is that really shows number 4 is twice of number 2. That's it. So it shows how close there are a bunch of them together and how far is that. If you just don't put anything, then I don't know really is it log and so on. So it doesn't have
you
any
could
physical.
erase the numbers and still have the same information.
But
yes.
Exactly. But the ticks should be there.
Yes, you need the tick marks. I don't know that. So, if I want
it depends a bit on how you're doing this and how you define your misfit functions. But if you just, so I have some other plot which starts with a random normal distribution of all those 1,000 points, and it depends. So the numbers depend on the variance of that normal distribution. So it's not as clear as in PCA, where you can say this is my first principal component, this is my second principal component. It's because this is because the PCA 2 dimensions. So the 2 first eigenvalues of the PCA don't explain all the variance in my high dimensions. So therefore, I could use 3, even 3 explain, I think, for this case, only 65% of the variance. And then when I go to 4, I have the problem that I can't plot them anymore.
Nico,
yes.
I'm thinking, based on the conversation for the past few minutes, one of the underlying things that's being done is that you are adjusting the points in the 2-dimensional space to get equivalency between the correlation covariance matrices from in the high
Not
dimensional
between the covariance, between the distance matrices.
the distance
Between the
matrices. So
distances, yes.
maybe it would be good to show, say, the initial case, and then maybe a couple of examples close to convergence, just so you can illustrate
Yes.
the organization of the map.
Yeah. Steve.
I wonder if I could just ask for a point of clarification here. Norm said a minute ago that if you're given a new ground motion model, it's not possible to plot it on a pre-existing salmon map.
I did not say that.
That's the
Yes,
clarification I wanted.
No.
Well,
Does it require, if I add a point, do I have to regenerate the entire map in order to plot that point?
That depends on the method you use. So for Salmon's map, you need to recompute everything. I mean, if you do PCA, for example, you could actually do that, but then you wouldn't just, for 2 dimensions, you wouldn't be able to really capture everything. There are other methods, and I haven't shown them here because they're a bit more, even more complicated, and where you can do that, where you can actually take a new point, plot them onto the map.
But for the salmon map, the manifold actually changes when you add another point, and so you just...
It's not that the manifold changes, it's just that
The optimized points would change. But if you have 1,000, then the structure is pretty well set.
Yes.
So if
Yeah,
I add
right.
one more to this, so we can bring in Grazer and Calcon, or we can bring in the simulations and put them on here without the map jostling all around because you have so many already setting the structure.
No, I just asked it as a point in principle to help me understand what's actually being done. So
What I was
things do move a little bit, but not,
Right.
but the structure doesn't change.
What I was trying to say is, if I just had a GMPE and nothing else, I can't, there's no equation that tells me, oh, okay, Cho and Young's, that plot's at -2 plus, at a certain coordinate on this system. I can't calculate that. It's all of an optimized way of their relative positions that mimics the distance space in the higher dimensional.
But it sounds to me like it's a little bit more fundamental, that actually you couldn't place it on there and still have a consistent salmon map. You'd actually have to recompute it and let things jostle
But I
just a
guess
little
I'm
bit
saying,
to accommodate it.
starting from scratch, I have nothing. I have a blank page. Where do I put model 1?
Sure. Oh, yeah,
Okay,
that's clear.
there's no equation that says here goes this one, here goes that one,
Right.
in the way I've created it.
Yes.
But once you have it, then it's going to fall into its natural spot, right? So,
Yes.
and if you readjusted it, it's not going to move things very much.
Not going to move things very much, but just as a matter of principle, it does
could
move
move it,
them
right.
a little bit, correct? Okay, thank you.
Probably, yes.
I guess in doing this, you could force all of the ones here to stay the same and put the new one at its optimum location relative to that.
yes.
So
Yes,
you
you
could
could do
hold it
that,
fixed, right? Okay, so I think this review was necessary, and I'm glad we did it again. So I hope you're all going to pass the quiz at the end of the day.